In our course on information theory in self-organization and complex systems, we're going to start at the very start. What I mean by that is we're first going to consider entropy, the fundamental measure of information theory, and that is the focus of our first lecture here. This first video is going to talk about our motivation for studying information theory in complex systems in the first place. So let's recall where we've come across concepts of information before when we've been talking about complex systems. Now, obviously, a lot of you will have encountered these concepts in different areas of your reading and in the work that you've been doing. I'm going to focus on where we've come from at the University of Sydney, where we've come across these concepts in an earlier course, Introduction to Complex Systems, CSIS 5010, that some of you may have undertaken. Now there we talked about information processing in biological systems, how we could think about the birds in a flock, for example, computing their collective heading, how we could think about ants as computing the most efficient route to food, and how we can think about collectives of neurons computing thought effectively. We also came across concepts of order and randomness, and concepts of information seem to be underpinning those. We talked about the concept of the edge of chaos, how many complex systems seem to be at a phase transition between ordered and chaotic activity, and including elements of both, and how there were many conjectures about systems near that point maximizing information processing capabilities. We talked about the concept of self-organization being defined as an increase in order over time, in particular without external control, and you can read more about that in Siyama's excellent text. Similarly, we talked about emergence as an increase in order over scale. Again, you can read more about that in Siyama. In both cases, we talked about these concepts and how they increase, but we didn't really talk about how to measure them. Later on, we're going to look at using information theory as our way of measuring the structure in complex systems and a way to define these concepts. We also talked about the differences between order and disorder. We talked about ordered systems, which have fewer outcomes at system level, seem to have less uncertainty and less information in which outcome we're observing. We talked about disordered or random systems, which have more outcomes at system level, seem to have more uncertainty in terms of what we're observing and more information contained in them. We talked in general then about how lower probability states of a system are more surprising to us as observers and carry more information. Again, we didn't really strictly define what we meant there yet. So as I say, we talked on and off about how complex systems process information, but we didn't really specifically define how to measure it yet. One more quote that I want to share with you is a very nice one from Murray Gell-Mann, who was one of the founders of complex systems science and indeed a Nobel laureate. He said, although they, complex adaptive systems, differ widely in their physical attributes, they resemble one another in the way they handle information. That feature is perhaps the best starting point for exploring how they operate. That's exactly the standpoint we're taking in this course about using information theory to analyze complex systems. So in order to quantify all of these key concepts, we're turning to information theory. So before we get started, I want to go over some of the learning outcomes that we've set out for this course on information theory and complex systems. At a very basic level, I want you to understand the measures of information theory, the basic measures as well as more advanced measures for time series, and how we're going to use these to analyze and dissect the nature, structure, function, and evolution of complex systems. More important than just understanding these measures though, I want you to be able to apply them. So we're going to develop scientific programming skills which can be applied to empirical complex system analysis as well as design. I want you to have the ability in applying these measures to make informed decisions about how you're going to do so. Which tools, which measures of information theory you are going to select for your analysis. How can you answer the question that you want to ask about your system with information theory? as well as that to be able to choose which software tools to analyze complex systems, and in particular, which type of estimator and how to use it is appropriate for this analysis. More than that, we'll be teaching you to create analyses of your own real-world data sets, in particular, to be able to conduct empirical analysis on data sets from your own domain area of expertise. So not just to take a small piece of analysis and answer a question someone else has given to you, but how to form the questions that information theory can help you to ask about your own systems. I also want you to have the ability to critically evaluate what you are doing in using information theory for analysis here, as well as what others are doing, and how you can evaluate the insights that are provided. What are the limitations of the analysis? Where does information theory work better in answering questions than for other questions, and so on. And finally, as I say, we're focusing on empirical analysis, so I want you to be able to understand the design and to extend the design of software for such analysis using the techniques we've learned in class and from your own readings. Okay, so in our first lecture here on an introduction to information theory and entropy, the things that I want you to take away from this are in particular to be able to express ideas about uncertainty and information. As we'll cover, uncertainty and information are two sides of the same coin. We'll talk about how to measure both. I want you to understand the fundamental measures of information theory. In this lecture, we're going to start with entropy, joint entropy, and conditional entropy. And you'll also be able to partly construct MATLAB code to compute these measures and apply that code to examples. We're not specifically going to do that in the lectures. That's in the activities that we'll thread through here. Finally, let me point out that the primary references for this lecture are they're basically the four primary references for our course. Cover and Thomas, Mackay, Bossemeyer et al., and my JIDT introduction paper. What I've done in the course materials, the reading list is showing you which sections out of these four apply to this lecture. Essentially, they're all getting you to the same point. You can pick any one of them to give yourself some background reading on this material. If you've got time, you may find it useful to compare between them because they will take different perspectives here. Obviously, my own perspective is about using these for complex systems analysis, and that probably aligns slightly better with the course, but you may be interested in particular to see probably the traditional sense given by Cover and Thomas and Mackay here as well for comparison.